Magnetic switches are everywhere. Door sensors, headphone cases, and laptops.
They're even in our water meters.
And the physics behind them is fascinating. So today, we're going to dig into the Hall effect and the circuitry that turns it into something useful. We'll talk about how Hall effect switches match up against other types of switches and how and why these switches and latches get used in designs today. In this tech chat, sponsored by Mouser Electronics, we'll be guided by an expert in this field, Mike Falter, Product Marketing Manager for Magnetic Switches and Latches at Allegro MicroSystems. Mike, thanks for being here today. I'm excited for this.
Yeah, no, I am too. Yeah, this is going to be good.
So I'm curious, you are around these day in and day out. Where do you see low power magnetic switches getting used in the industry?
Really low power magnetic switches can be used everywhere. So you see a proliferation of battery powered devices, IoT devices, consumer electronics, wearables, and magnetic switches and latches are great non-contact sensing solution. They can use for all kinds of motor control, open, close, detect applications across all of those battery powered devices. And it's a great sensor solution. And at Allegro, we've really leveraged our technology to develop a high performance, low cost, and very low power sensing solution.
And I want to get into more of the kind of pros and cons versus magnetic versus reed versus like physical contact switches. But first, I'd like to dig a little bit into the physics of this. Can you explain to me what is the Hall effect? How does it work?
Yeah, so the Hall effect, based on the physics, it's the Lorentz force. And the Lorentz force is just a force on any current-carrying conductor in the presence of a magnetic field will generate a force on that conductor that is normal perpendicular to the magnetic field. And so we use that in our magnetic switch Hall sensors. We use that concept to create a sensor. And you can see on the bottom diagram here, what we do is we have a Hall sensor or a Hall plate, and we'll bias that with a current. And the current is basically charge. And when that sensor detects the magnetic field, the charge is displaced across the surface of that sensor, and that generates a voltage potential. And that voltage potential is linear and proportional to the strength of the magnetic field. Hence, you have an excellent way of detecting a magnetic field and generating a voltage that you can process a signal off of. Yeah.
So it's not necessarily just on and off. You can actually tell if you know the strength of the magnet and you know the strength of your bias current, you can essentially characterize the distance from the magnet to the plate?
Absolutely. So if you look at Allegro's larger portfolio beyond just switches and latches are what we call digital output devices. So to your question, Dan, those devices do have either an on or off, yes or no, but you can do a lot more. So we have also 1D linear sensors that can detect linear range, and there's all kinds of sophisticated algorithms that we can incorporate to process that signal coming off the Hall sensor. Today's discussion, we want to focus really on the digital output switch and latch, which is the fundamental building block for magnetic sensors.
To kind of repeat what you said about how the Hall effect works, the way I kind of envision it, and correct me if I'm wrong, you have the plate, you have the current going through it, and as soon as you have a magnetic field come in, that magnetic field essentially like squishes electrons to one side and maybe holes to the other side. So now you have a difference in voltage or a potential difference between those two parts of the plate. And the stronger the magnetic field, the more it's going to kind of squish those over and give you a stronger voltage.
You can imagine a flat plate and you have two nodes, a high voltage and a low voltage generates a current across that plate. Yeah, the charge within that current flow gets shifted, left or right across that. And just as you said, the shifting electrons creates a potential that can be measured and is proportional to the magnetic field. Yes, so exactly as you said.
We just talked about switches. Can you tell me a little more about what these things are detecting? Are there limitations to orientation?
So the idea with a magnetic Hall switch is that it's detecting, and we'll talk a little bit about the inner workings of the IC in a second, but at the highest level, it's simply detecting the presence of a magnetic field or not. Typically, that's actually a magnet that generates the field, but could be electromagnetic sources. And in the case of switches, again, it's a digital output, so it's either a high, low, yes, no. So if the magnetic field exceed the internal threshold of the device, it'll output one state, high or low. And then once that magnetic field strength drops below a certain threshold, it'll change state. So it's just detecting basically, is the magnetic field exceeding a certain threshold or not? And it will provide the system information on that. So it's great for lots of open close detect, position detect, motion, and it does it in a non-contact, highly reliable solid state manner.
I was even reading about some like gaming keyboard switches where you could control the strike depth based on how far the key was pressed. You could essentially, like with the firmware of the keyboard, control it. And I assume this is probably like threshold triggering to turn the switch 1 or 0.
Absolutely. So it could be threshold triggering. So that's the yes or no. Is it on or off? But in some cases, we talked about some of the linear devices that are not just digital output, but will put in maybe an analog output voltage that's linear to the actual strength of the field, where you can actually get more information to the computer for the keyboard or the gaming interface, wherever the device might be, to provide an extra layer of interface. But both of those use cases, are very similar, coming off the fundamental principle of the Hall effect sensor.
And then when you compare a Hall effect switch to something like a reed switch or a micro switch, can you walk me through, like, based on this chart, the Hall effect looks amazing. When would you choose one over the other?
Yeah, so, magnetic sensing technology has been around for a while. I think some of the innovation here is really taking the power out of it. A Hall effect switch, it's really a solid state switch. So compared to a micro switch, there's no mechanical moving parts. So that introduces a much higher level of reliability. Same for magnetic reed switches, which have been used, widely across many applications and industries for many years. Although they're magnetically actuated and non-contact, there's still mechanical moving parts, so that creates some reliability issues. So I think by using a solid-state Hall sensor, you eliminate any moving parts. So that really increases the long-term reliability. Some other advantages are the technology. It's all built onto a single monolithic chip with the Hall sensor, so it can be very, very small. And we were looking at some chip scale bump die type packaging. So compared to micro switches and reeds, you get to a much smaller form factor. And I would argue in many cases even a lower cost, as we leverage the latest technologies to drive down wafer prices and assembly costs. We're getting very cost competitive. And then today we're talking about low power. So micro switches, reed switches essentially in many cases don't consume power. So that would be one weakness of the Hall sensor. We're rapidly eliminating that weakness through some of our design initiatives to develop these Micropower Hall switches.
So you mentioned these are going into monolithic ICs, so it's not just the Hall sensor portion of it. There's a lot of other things happening. Can you talk me through what it takes to make a good low-power Hall switch?
Yeah, absolutely. So monolithic IC means we build up the circuit on the silicon wafer, the N and P-doped devices, and then the Hall plate is built on that as well into the individual IC on the wafer. So it's very compact. And so basically, magnetic Hall switch IC is a monolithic IC with the Hall plate built right on top of it. And it has the bias current like we talked about that, again, shifts according to the strength of the magnetic field that it detects. And then that introduces the voltage on the plate of the Hall sensor that's right part of that integrated IC. It's packaged in the packaging, and then sends that signal to the integrated circuit. So in this case, there's usually some preamplification. We have some offset cancellation circuitry that takes that very small voltage, amplifies it and conditions it, removes any of the offsets, and then passes that on to some comparator circuitry. So recall we talked about some of the magnetic operating thresholds. So that's all programmed into comparator circuitry within the IC that determines yes or no, it's exceeded a certain threshold. And then the last part we have here is you have an output stage. And so that takes the sense magnetic field and converts that to either a high output or a low output, depending on what's sensed, and drives the subsequent load, or maybe provides a signal to the downstream MCU to convey the sensor status to the system. And then to the right, you can see kind of a printout of what one of these integrated circuits would look like, with the Hall sensor in red actually embedded right into it. So all one single unit. And by having that, you look at more efficient design, better performance, lower cost, not having to use a multi-chip assembly.
So I want to come back to some of these elements in the block diagram because I suspect there's some very clever stuff happening here. But is this chip then going into its own package? Is it going as a chiplet format? Kind of how do these get deployed into actual systems?
Yeah, so typically the magnetic switches come in two main package types. There's the SOT23, which is a surface mount package. It's a 3-pin package. And I forgot to mention on the prior slide, you usually have supply pin, ground, and an output. So it's a very simple 3-terminal device. And so it's a surface mount SOT23, extremely small. We also have through-hole SIP, 3-lead SIP packages. And typically, in most cases, a one-dimension sensing device will sense on the Z-axis, and it'll sense magnetic fields that are perpendicular to the top marking on the IC, whether that's the 3-lead SIP or the SOT23. But our sensors can detect more than one axis. So we have devices that have both vertical hulls and planar hulls so that we can detect in 1, 2, or 3 axes, X, Y, and Z, and that's what we're showing here on the bottom left. And historically, the SOT23 and the 3-lead SIP have been kind of the mainstays of the magnetic sensor switch market. But we're seeing more in terms of DFN, smaller DFN type packaging, and also, as I mentioned earlier, even bump die. We'll skip packaging altogether, and we'll run that wafer through a bumping process and then singulate and ship just as a bump die. So that can, in addition to reducing the size significantly, can also actually save us a little bit of cost if customers' manufacturing capability can handle that smaller pitch of a chip scale. But honestly, Dan, I think that's where the market's going. Everything's getting smaller, cheaper, more compact, more electronics in smaller spaces. So that's where we think the market's moving.
So will people then take the bumped die and integrate it into their die and then package the whole thing together? Or what are they doing with the bumped die? Is it just kind of going raw on the circuit board?
They could do that, or they could place it right on their PCB. For the switch sensor, it's really a paired solution. So customers trying to detect, again, position, proximity. Just an example would be a notebook computer lid. Maybe rotating a rotor and a DC motor. So it depends just on where they can put the magnet for the device that they're trying to sense versus where they have to put the Hall switch. And I think in many cases, for a bump die example, just be populated right on the PCB. And then just some pretty sophisticated math and analysis in terms of the size of the magnet, the magnetic material, the distances, and the field strengths that's going to create on the sensor to make sure you're getting the right system operation. And, when you get close enough proximity, that's the signal you want to generate. So there's very much along with the electronics, there's very much a mechanical component to designing with these devices.
Do people typically order like a dev kit for this, or are there calculators or simulation tools? If I wanted to put one of these on my board as, say, a limit switch, how would I go about choosing a companion magnet to go with it?
Yeah, so we have, in addition to a great team of sales applications engineers and internal systems engineers within Allegro, we also have a lot of applications, notes, and resources on our website that provide guidance specifically on magnet types, sizes, field strengths, how different magnets create different types of fields. And that's a great starting point. We also have some tools with some partners, or I believe you can go and generate some graphs for different magnet sizes and types that can show the associated field. And that's a good starting point. And I expect in many cases that kind of gets you halfway there, but at the end of the day, you probably have to build a prototype, get some magnets you think look about right, and kind of just work with it in the lab and kind of see what fits, and then just kind of refine it from there. And then get to the solution that works.
So looking back at the block diagram, I noticed there's a Schmidt trigger in here, among other things. And when I look at the thresholds here, there's essentially some hysteresis. I assume this is to avoid chatter. Can you talk me through this chart?
100%. Yes. I mean, so for a switch and latch digital output device, you want a yes or no answer, as it met the threshold in terms of proximity, position. Let's say I have a device that maybe I'm detecting a window position and it's right there. You don't want you chatter. You don't want it bouncing back and forth. You want a definitive yes or no. And that hysteresis, in a lot of designs gives you a little bit of margin there to differentiate between the two states. So that's exactly what we have in there.
And then it looks like one is like 0 to, a positive magnetic field. So that would maybe be proximity. When would you use the latch configuration for like a negative to positive situation?
Yeah. So I think maybe to answer, that's a great question. Maybe to answer that, maybe I'll just kind of go over the fundamentals between the two because they're both magnetic sensors. Well, unless you work with the technology every day, it can be a little confusing. What is a switch? What is a latch? But I think these two diagrams we're showing here do a really good job of illustrating the difference between the two. Basically, a switch is a magnetic sensor that operates off a single polarity magnetic field. So here we have a nominal south polarity magnetic field. And what happens when the magnetic field exceeds the operating point threshold, it changes state, in this case going high. And then once you remove that magnetic field, the switch changes state again. And that's the release point with the hysteresis we just talked about. And the output goes low. So that's the switch. The only difference with the product on the right, which is the latch, which is also called a bipolar switch, is that instead of just operating off a single polarity magnetic field, it operates off both polarities. So here we have the B plus or the south polarity field triggers the operating point. But to get the latch to change state, you need to apply, not just take the magnetic field away, you need to apply a magnetic field of an opposite polarity in typical similar magnitude to cross that release point and get the device to change state. And to your earlier question, so when do you use the two? So switches are great for like open close detect. Where latches really do well is when you have rotating machinery. So almost any brush DC motor, brushless DC motor, there's a good chance it has some kind of a Hall sensor for its position speed sensing. And in the case of brushless DC motors, for its motor commutation. So in a brushless DC motor, you have a rotating magnetic field through stator windings, and the motor controller will control how the sequencing of the excitation of those windings. But to do that correctly, you need to know where your rotor is. And so the rotor will usually have magnets, rotary magnets embedded in it. And then you'll typically have a series 3 Hall sensors that are detecting the magnetics coming off of that rotor and can determine the position of that rotor, communicate that to the control circuitry so that you get good torque and good performance on that DC motor. And that's where it's really a kind of a sinusoidal waveform where you want to have the latch behavior versus the switch. So you always have a positive indication of the position of that rotor. So that's a really good example of where you'd want to use a latch.
Let's talk about the output block of the circuitry. It looks like there's maybe an external pull-up or pull-down resistor and some other stuff happening here. Can you talk me through the output stage?
Yeah, for most of our Hall switches, kind of the default, the traditional output stage is a single open drain FET, and that configuration requires a pull-up resistor. When the output turns on, the FET turns on, the pull-up resistor pulls the output down through the pull-up resistor. When the FET is off, it pulls the output high. So that's how you have that high and low output mechanism through the internal FET and that pull-up resistor. That's a great solution. You can typically drive 20 milliamps of current, so you can drive loads beyond just a microcontroller. It's very fast. But where it falls a little bit short is when we started this conversation, we start talking about battery-powered IoT devices, meters that need to operate in the field for 10 years. That pull-up resistor isn't always the most power efficient, right? So you have I squared R losses when that device is on. So you need to look at really an alternative output stage. And so one of the design techniques that we use for our Micropower switches is a push-pull output. And so that's, instead of having the single FET, we'll have a high side, low side FET. And that way we can source and sync current from the load through the FETs. And that eliminates the need for that pull-up resistor and the associated I squared R loss. So it ends up being a much more power efficient solution, which is really a design goal. Now, there are trade-offs. It's not free. So typically the response time might not be as fast, and the drive currents are really on the order of 1 to 5 milliamps versus 20 milliamps. But if you think about micropower applications, IoT devices, wearables, typically they're lower bandwidth, and they're not really high power loads, and they're pretty simple circuits. So it's a few sensors and a microcontroller, so very efficient. So if you look at the end use cases for these devices, the push-pull output stage really is a great fit.
That makes sense. Like if you're trying to actually drive something maybe electromechanical out of it, this is not going to necessarily kill your battery life. But if you are doing something that requires smaller power outputs, then you can use the other configuration and it works just fine.
Exactly, yeah. And if you're trying to drive some large load, chances are it's not a wearable.
Right.
Chances are it's not some IoT device. So, but we're always trying to push the boundaries and innovate. So,
on the topic of conserving power, I also saw there was like a sampling and hold block in that circuitry. It looks like you're doing some like just instead of keeping it on all the time, there's a sleep period in here. Can you talk me through what's happening?
Yeah, so let me talk about the sleep period, but just to come back to the sample and hold. The sample and hold is actually part of the offset cancellation. And so just to really touch on that. So it's really kind of a cool circuit. So what it does is it any kind of low frequency DC offsets or offsets maybe you push on the package gets chopped up to about 800 kilohertz, and then it gets modulated down and filtered out. So don't ask me to explain the circuit, but it's a pretty cool way of modulating with the high frequency, then filtering out some of the offsets, eliminates a lot of trim circuitry and gets you more precise outputs. So it's kind of a cool circuit. So that's the kind of the sample and hold. And then in terms of the Micropower, what we do is what we use is called duty cycling. So if you look at, for example, the APS 11753, which is our most recently released Micropower Hall switch, we just released that in January. That actually has an operating supply power consumption of about 1.5 milliamps, which is not a huge amount of power, but we wouldn't say that's micropower. So what we actually do is we pretty heavily duty cycle it. So if you look at the operating period of that device, we have an awake time or a sense time. It's only about 60 microseconds. So it only takes 60 microseconds for us to turn the IC on and detect and measure the voltage off that Hall sensor and communicate that through the system. And then we go to a sleep state. And that sleep state is on the order of 50 to 60 milliseconds. So most of the time, the device is in its low-powered sleep state, which is just a few microamps. So the net effect by using that heavy-duty cycling is that we can get to a continuous power consumption of under 5 microamps, which is really what you're looking at. So only waking up that sensor for very short periods of time to get the measurement, and then conserving the battery life.
Yeah, that's orders of magnitude difference between the sleep time and the on time. So I could see that averaging pretty small.
Absolutely, yeah, yep. And it makes sense because a lot of the applications, open close detect applications, field applications are, not the highest bandwidth. 20 hertz, 50 hertz, 100 hertz. So you don't really need to be continuously monitoring. If you're monitoring that signal every 20 hertz 20 times a second, that's plenty fast for a wide range of these low power applications.
So there's clearly some very clever stuff happening inside of these. Can you tell me more about Allegro's specific offerings of Hall switches?
Yeah, I wanted to take this opportunity to talk about some of our latest Micropower switch and latch offerings, the APS 11753 and 12753. So these just released in January. They're available to order now. Again, the key features are the ultra low power. We talked about the duty cycling that we use to get to a continuous power consumption of sub 5 microamps. And these parts are designed to operate on a single supply voltage of 3.3 volts and less. So really great for any battery-powered applications. I wanted to mention that through the techniques I just talked about, the push-pull output, the duty cycling, also a lot of innovations we've done in terms of our IC technology and packaging, we've been able to reduce the power consumption by over 50% compared to prior generation parts. So that's great. And we really haven't had to sacrifice performance. So we still offer a lot of design flexibility in terms of wide range of magnetic switch points. And by the way, if you recall the conversation of the duty cycling, we have some flexibility there. So you can actually select parts with different sleep types. So if you want to trade off power consumption for frequency response, you can go to, the 5 microamps to maybe 100 microamps or higher, a little higher, to be able to sample that magnetic field at a higher pace depending on what the requirements of your application. That just offers a broader range of design flexibility. And again, like everything else, with a lot of these consumer electronics, medical wearables, IoT devices, we're talking very large numbers for a lot of these OEMs and manufacturers. And so they want good value. And so we've used all of our manufacturing technology, design capabilities to design for value so that we can help our customers meet, their BOM cost targets to meet their end solution costs for their customers. So it's about delivering performance, delivering value, preserving battery life.
So we've touched on this a little bit, but can you tell me more about where you're seeing these being implemented? Who's actually using these in their designs?
These switches are used in a wide range of applications. Security systems for window open-close detection, personal electronics, charging cases for personal electronics, lid detect. But one application also is utility metering. So this is a great use case. Water and gas metering, we're seeing a transition to automatic meter reading and smart meters. So it really starts with a radio and an MCU so that you don't need to manually read these meters. And then once you have the MCU and the radio and you have the battery, you now have the capability to build more intelligence. So in terms of water and gas metering, a magnetic sensor is a great solid state solution. So instead of a mechanical meter interface, these meters typically have a propeller or an impeller that rotates as the gas or water goes through the meter. And what you can use is you can put a small magnet on the rotor, and then external in the housing, you can incorporate the magnetic switch. And that switch can then detect each time that impeller or that rotor passes, and you can generate a pulse train. And then that pulse train is going to be proportional to both the velocity of the impeller and the meter, water or gas. And then you can determine how many rotations and how fast, and that way, knowing the mechanics of that meter, flow rates, etc., you can determine how much usage was done by that customer, whether that's water or gas. And then you have your smart meter, which can go right to the MCU, do all kinds of other kinds of intelligent, neat things in terms of energy, gas, water usage, and then communicate via that short-range wire, short-range radio, or even long-range radio, to that utility operator or to the apartment operator to understand what that usage is. So this is a great use case for it. And if you look at these applications, they're high-volume applications. They need to be cost-efficient, value-driven. You deploy a smart meter, needs to be in the field for 10+ years on a single battery. So it needs to be very power efficient, so low power and low cost. Those are real value drivers. And so a magnetic Hall switch like the 11753 is a great option for that type of an application.
I really want to go take apart my water meter now. I will resist the urge and maybe just look up the specs online. But that is really an interesting use case of these. If someone wanted to integrate these into their systems, what's the best way for them to get started with the Allegro chipset?
Yeah, I think the best way is to, can reach out to us, can reach out to one of our distribution partners like Mouser, get a sample, get a data sheet. We have a wide range of app notes that cover all of these applications. So we have a white paper coming out now on how to use magnetic sensors for electricity, water, and gas metering applications, tamper detection in electricity meters. And then from there, just educate yourself and start, looking at the large range of use cases and how they can be applied, to include, maybe building a prototype board, working with some of the magnetics and just getting in the lab and, trying to put the pieces together and formulate some ideas.
I'm curious about tamper detection because I saw a mention of that somewhere else too. Is that kind of like a, seal, warranty void if seal's broken sort of thing, or what does tamper detection look like in this context?
So in electricity metering, there's usually a kind of current transformer mechanism that will meter the amount of electricity. And what people have done is they've taken large magnets and actually put them in close proximity to the electricity meter or even attach it to the electricity meter.
Okay.
And that basically blinds the current sensor. So the meter doesn't know that, it's basically free electricity. The meter doesn't know that because this huge magnet is swamping your current sensor. So the Hall sensors, and usually this is a 3D solution, so it could either be 3 Hall sensors, or I mentioned the the 3D Hall sensor, is separate from that and can detect when that meter is being tampered with. So if the Hall sensor detects an external magnet that exceeds a certain threshold, is, hey, somebody's trying to tamper with that meter, and we can send somebody out to look at the meter or figure out what's going on. Maybe there's some issues. So that's a way to detect that kind of a situation. Yeah.
Interesting. That's very clever. But don't break the law, kids.
Don't break the law. Yeah.
Another place I know I've seen these a lot is for like doors and windows. You mentioned them a little bit earlier. Can you give me the kind of high level view of how these work?
Yeah, absolutely. So in security or HVAC climate control systems, you want to know the status of doors and windows in a system or in a building, particularly for security, and when the windows are closed and the doors are closed. So magnetic switch sensor is a great tool for this kind of an application. So here, in this case, what you do is you'd embed a magnet in the door or the window. And then in the windowsill or the door frame, you would have an RF IoT sensor, MCU, small radio, and you would embed the magnetic switch sensor. And then that switch sensor can detect when the window closes and the magnet comes in close proximity to that IoT module. It'll transmit to your security system or maybe your environmental control system that window or door is shut. With our solution, again, it's a digital out solution, very simple, a magnet, the switch on the IoT module, and just a direct connection to the I/O on the MCU. And you have a 100% reliable, small, and cost-effective way to confirm that a door or window is closed or open.
I love a simple but elegant design.
Simple but elegant, yes. Highly complex physics, pretty simple application.
Well, Mike, this has been wonderful. Thank you so much for your time today.
Yeah, thank you. It's been great. Appreciate it.
Thanks for tuning in to this tech chat brought to you by Mouser Electronics. That was Mike Falter from Allegro. And if you'd like to learn more or get some of these for your next project, use this QR code or head to mouser.com/Allegro. I'm Daniel Bogdanoff, and I'll see you next time.